Good morning, everyone. Can everyone hear me? There's supposed to be a kind of mic here. I hope you all had fun yesterday with the math lecture because you're gonna need it this lecture. So this is the first proper physics lecture that you're going to have, and yeah, I hope you all are excited for it. All right, so I guess I think you all of you here have a basic idea of what quantum mechanics is, and you also know what the kind of physics that you learn at school is it's charged by XKCD is over here. It's boring. It's a lot of incline, do stuff like what else do you do in JC? Static charges, kinematics and stuff, and yada yada yada. And it's not really exciting, and I guess that's one of the reasons why you want to know more about quantum mechanics is because at least in popular science, it's one of those exciting words that are used in all things, in a lot of like science fiction movie by that I mean, and it's something that if you come to the philosophy discussion circle yesterday, you might have learned also that it has some interesting philosophical meanings, and it's also very difficult mathematically compared to some other branches of physics. So there's a lot of misconceptions that arises in quantum mechanics because it is exciting and because it is difficult. So in this lecture, I hope that we are going to be able to set up a solid foundation on what QM actually is. You might have heard that, okay, I just said it myself. You might have heard that QM is weird, it doesn't make sense, and learning about it can be very counterintuitive sometimes. Like this funny meme that I found in Reddit 1 year ago. Yeah, but I'm telling you, I was reading this article weeks ago that actually argues that QM is not actually weird. Like, it is a bit counterintuitive, but people have been saying that QM is weird to a point where new students think that they are not supposed to be able to have an intuition about QM. But that's not actually true. Our mathematical formalism actually has a lot of strength in prediction for quantum mechanical systems. So actually, we kind of have a good grasp of what is happening in quantum physics. It's just that it can be a bit weird sometimes, especially in the beginning, because we are not used to think in that way, in that paradigm, because we are so used to the classical world, which is basically everything you can see with your own eyes, that the things that happens at this level can be a bit foreign in the beginning. So as I mentioned, the goal is to build a solid foundation for the next few lectures. And the things that we're going to talk about, you might have heard of them before. First is superposition, then the Born's rule and operator. We learn about it when we come to it. And I'm gonna try to avoid talking things that are more metaphysics, things like the interpretation of quantum mechanics and stuff. We're just gonna stick with the textbook math for this lecture. And math, there's gonna be math for this lecture and the next few lectures. So I hope you haven't regretted your decision to sign up. So we're gonna have a basic the outline of the lecture is gonna be simple. We're gonna start with the qubit. What's a qubit? Then measurements, then some more conceptual discussion and operators. But anyway, what is a qubit? Does anyone here know what a qubit is? Okay, good. Just to make sure. So first of all, what was quantum mechanics in itself? I guess Alex has explained to you. Yes, at least he gave you an idea of what quantum mechanics is. It's basically physics at very small scales. It's not really true, but it's basically physics at really small scale, at the scale of atoms and smaller. Because at this scale, things start to behave differently. The physics that we use, like Newton's law and stuff, starts to not fully capture the dynamics of what's happening down there. So that's why we need a new theory. And in this lecture, we're going to focus on qubit mostly, actually for the whole of it. And the qubit is a shorthand for quantum bit. In physical terms, it's a quantum mechanical system that is composed of two physically distinguishable levels. What do I mean by this? It's easier if we go to the examples. But remember that it's a two-level system. So it's a quantum system and it has two physically distinguishable levels. For example, one of the more intuitive one, famous one is a spin particle. You know about electrons, right? And neutrons is a spin half, right? Neutrons and protons. You might have heard that they have this property called the spin. Sometimes you can just think of it as it's a magnetic moment that the particle has, that this elementary particle has, like electron. It has it's called spin half for a long reason, but basically the spin is a vector, so it has a direction, and if we define a z-axis, and then we measure the spin along that direction, there are only two possibilities of where that spin is pointing, either pointing up or pointing down. So those are the two levels here, is the spin pointing up or spin pointing down. At this level, it's not really necessary to talk about why there's only two levels and why is it called spin half and what's a magnetic moment actually. But anyway, like there's this factor that points up or down when you measure it for certain elementary particles. So that's one example of a two-level quantum system. It's a quantum system because it's small. It's like elementary electron and it has two levels. Another example is photons or light particles, as will be described by Junsheng in the next lecture. But basically, there's another way to think about light as a qubit is in the direction of polarization. So you might have known that light can be described as a wave, and a wave wiggles, and it wiggles in a certain direction. Then the direction of that wiggling is called the polarization. And so you can imagine that if a wave is traveling from here to here, it can wiggle in the horizontal direction or the vertical direction. But those are the two physically distinguishable states for a photon. Okay, so there are more. Transpond. What's a transpond? Is a thing in the superconducting computers. It's basically an artificial atom, so these things are basically the same, basically. So like it's in an atom, you have an electron and a proton, and the electron can, if you took chemistry, you know that the electron has different orbitals and stuff. Actually, don't know, but I've forgotten my chemistry. But basically, there are different levels that the electron can be placed in, and these energy levels. Well, if you close your eyes and only look at two of them, there are only two energy levels, and so those are the physically distinguishable states in the case of an atom. And it's a quantum system again because it's an atom. And also something bigger than an atom, like light. So in the lab, you have this thing called the beam splitter, in which if you send in one photon, it has a 50-50% chance of going in one direction or the other. So in this case, the two physically distinguishable states are either the light coming out of output or the light coming in at that output. And even though it's bigger than an atom, like a beam splitter is an actual thing you can see with your own eyes, it can still be described by a quantum system given the correct circumstances. So, and there are other examples. I mean, Lisa mentioned the Stern-Gerlach yesterday. There's also an example of a two-level system. So from this point on, we're not. I'll be mostly talking in mathematical language. But I just want you to know that whatever we're talking later, it's describing a physical system, and the physical system in itself can be of many different forms. And it's actually quite wonderful that we can describe these things that might seem completely unrelated to each other with the same formalism. But that's why we like to talk about two-level system abstractly, because you can actually implement it in the lab in many different forms. But they all can be described by the same math, more or less. So when we go into the actual math, I will still remember the linear algebra from yesterday. Because how do we actually describe the state of a system in a two-level quantum system? We describe it by a factor. Here we'll use the bracket notation. I hope you are comfortable with it. At least you can tolerate it. So because it's a two-level system, it lives in a two-dimensional complex Hilbert space. Yes. There's a lot of mumbo jumbo. Two-dimensional because they are. Oh, okay. Anyway, I'll write it later. Sorry. But basically, the state of one of the requirements that it must have is that it's normalized. Which means that if you take the inner product, the dot product, if you will, of the state and itself, you'll get one. So pictorially, it's like the length is one. And in this two-dimensional space, you must have a basis of dimension 2. And for conventional reason, we denote it as 0 and 1. And these bases are also like states, they must normalize to 1, and they must be orthogonal to each other. So they are called the orthonormal bases. And the 0, 1 we call the computational basis. And the 0 and 1 represents the states that are physically distinguishable. So for like the spin half particle, the 0 and 1 correspond to like spin up, spin down. For atomic energy levels, 0 and 1 correspond physically to like the ground, the electron being in the ground state, the lower energy level, and the excited state, the upper energy level. In the polarization, one of them refers to the horizontal polarization, the other one is a vertical. So you can kind of see how this notation, how this formalism generalized to actual. Basically, in different physical systems, the 0 and 1 denotes to different physical things, like the light coming out of the left output or the right output. But it's just notation. You can really just use anything inside the Brian cat. It doesn't really matter. As long as you stay consistent in your notation, this 0 and 1 itself, it's not a value, it's a notation. Yeah. How do we actually do calculation with them? We use matrices. So by convention, 0 is this factor here and 1 is this factor here. Might get confusing because in both of the matrices there are 1 and 0 inside. That's why, yes, I have to emphasize that this 0 and 1 is a notation that represents these factors. Now, you have factors, and you know you can add factors. When you add factors, you get another factors. The other factors we call superposition. It's another convention, but basically, if you add 0 and 1, or if you add 0 and 1, you get plus. If you add 0 minus, if you subtract 1 from 0, you get minus. The square root of 2 here, what's the purpose? The purpose is so that, I hope this works. Is that so that this is true, because in the first slide, as I mentioned, states must be normalized, which means that every state must have an inner product with itself of 1. You can quickly check this because you can see this, right? Can everyone see? Yeah, so let's just quickly do this calculation. So you get 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. Square root of 2 times square root of 2, you get 2. Now, because in slide 2, you'll see that this is 0. So and this is 1, this is 1. 1/2 plus 1/2 equals 1. So that's the reason for the square root of 2. Because if you don't have the square root of 2, you'll get 2 at the end. So if you write it down in matrix forms, easy enough, I think. So these states also have physical meanings. In the case of a spin 1/2 particle, so either in the case where the qubit is either a spin pointing down or spin pointing up, these states correspond to the spin pointing forward or the spin pointing backward. For other physical systems, the plus and minus also have physical correspondence, physical meaning, but it depends on the, we have to talk case by case depending on the physical system. But it's just a little semantic. We cannot call a state to be in the superposition full stop, because every state is a superposition in some other basis. So it depends on what basis are you talking about. If you're confused, just look at this example. Is 0 a superposition? You might think of it as no, because 0 is 0. There's no 1 in 0. So it's not an addition of 0 and 1. But you can write down 0, trust me, you can write down 0 as plus, cat plus, plus cat minus. So it's a superposition in the plus minus basis, because the plus minus basis is also a valid basis like the 0, 1 basis. So every state is a superposition in some basis. That's the point. If you don't get it, it's not that important. But generally speaking, other than plus and minus, you can make a lot of other superpositions. In general, you can write any state in a two-level system. You can write it as a sum of 0 and 1 with some coefficients, also called probability amplitudes. And A and B are a complex number, so you can have I inside of it. As long as the modulus of A squared plus the modulus of B squared comes up to 1. Why is this constraint here? We'll soon see in the measurement part. So measurement is another fun part of quantum mechanics, because it in classical physics we don't really talk about measurement, right? Nobody talks about the mathematical formalism of putting a ruler next to a table and measuring the length of a table. Because there's nothing really interesting happening there when you do it in real life. But in quantum mechanics, measurements happen a bit differently. As you might have heard before, there's inherent randomness in quantum mechanics. There are randomness in quantum mechanics, which means that we have to use probabilities. I hope you are comfortable with probabilities. It's a number between 0 and 1 that tells you how likely an event is. 1 means absolute likelihood it will happen. 0 means it's not going to happen, like, ever. And it has to be between 0 and 1. So that's basic probabilities. And so in an actual experiment, right? In an actual experiment, I'm a theorist, by the way, so I don't know what an actual experiment is. But from what I've heard, in an actual experiment, you have a system that you prepare, you evolve in some way, and then you do measurements on this system to get some result. Then from the statistics of the results, you make some analysis and judgment based on that. So the measurement part, where you have a system and then you measure it, is described by this Born's rule in quantum mechanics. So say that the system is in a state psi, generate cat psi, and then you are measuring either 0 or 1. Now the probability is given by the inner product of 0 and this psi. For the first slide, the probability of measuring 0 is given by the inner product of the state 0 and psi, and then taking the modulus squared. And for the other one, it's just 1. So you don't have to measure always in 0 and 1. You can measure in other bases, and if that's the case, you just replace this thing with the basis that you're measuring in. So for example, if you have this, if I give you the state plus, if you cannot see, please tell me. The probability of measuring 0 from this is you take the inner product and then you square it. So the inner product of 0 and plus is Yeah, I don't think people can actually see this, but
Maybe write it down.
yeah. So because plus is one over square root of 2 times 0 and 1. When you have inner product of 0 and 1, you get 0. And this one is 1. So it's 1 over square root of 2 squared. Oh. So it's a 50-50% chance of measuring 0 if I give you a plus tip. I hope you can follow the calculation. If not, you'll get a chance in the tutorial. So if we have a generic state A plus B, if you do the same calculation as this earlier, you will see that the coefficients come out here, and for measuring of the probability of measuring 0 from this state here will give you A squared. So the condition that A squared plus B squared equals to 1 is just the rule in probability that if you have multiple, if you have an event with multiple outcomes, when you sum up the probability of those outcomes, they must sum up to 1. For example, for a coin toss, the probability of head and tails must sum up to 1. That's the rule of probability.
Make time to do it.
Just to make the calculation a bit clearer, or I'm just going to do that calculation in the middle. So if we are calculating the inner product of 0 and psi, well, first we expand the psi. The psi is A. B1. So it's A 0 0. You open up the brackets. Again, this is 0. This is 1. So it's A. But I don't have the square here. So if we take the square, yes. Right hand side squared is the right hand side. So that's how you get that one. And for the second one, B, well, you'll see that for that one, this one will equal to 0 and this one will equal to 1.
For order of writing, there's 0 and the other symbol matters, like when you're doing calculations.
The order of writing. All right. It matters. The factors here, you cannot swap them. Yeah, you cannot just swap them. So A is a number, right? It's not a factor. It's a number. It's a scalar. The scalar you can just move wherever, but the factors you have to keep the ordering. So if I have this is not the same as this.
I mean, like the first step when you write the 0.
Zero sign.
Yeah, like at the very start, like your first expression.
This one?
Yeah, it doesn't matter if you swap it now. Right?
Oh, it
Does
matters.
any, like expression.
You mean this is in general not the same as this. It's actually the complex conjugate of the first one. So this is the same. Complex conjugate is if it's a matrix, you take the transpose and you change I to minus I.
Yeah.
It's just how it is.
Oh, okay. You have questions. So let's say you swap the two, the B and A's, right?
Mhm.
And you apply Bond's rule to it. Is it the same?
Oh, it's the same. Oh, in this calculation, it's the same because when you square it, right, the dagger symbol doesn't really matter. Yes. Sorry if there's the confusion. But technically, when you calculate things, sometimes you don't have the square, so in that case it will be different. So just to any other question of the calculation? Okay, so just to sum up, yeah, measurement, you take the inner, when you measure a qubit in a generic basis ij, you take the inner product and then you take the absolute value squared. And because we have an absolute value squared as we mentioned, the inner product here doesn't really matter if you flip it because there's a absolute value squared. And after the measurement, if this is the successful outcome, we know this, then the state will be in state. I will describe that later, but first of all, I just have 3 side notes here before we have a short break. The first of all is if I ask you the state plus and another state which is minus plus. So you take the matrix of plus. So if plus is written down as this, minus plus is just you multiply everything by -1. Are these two the same state or different states? The answer is, even though we write it down differently in the board, they are the same state. Physically speaking, they are the same state because when you take the Born's rule, for example, if you want to measure 0, right? If we want to measure 0 from this state, we take a dot product with like wrong marker. We take a dot product with 1, 0. And then we take the dot product, you'll see that this is 1/2. And when you take this state and you measure and you calculate the probability of measuring 0 from this, you take the dot product also. And you will see that you take out the 1 square root of 2 outside, you get 1/2. This one gives you -1 squared, 1/2. And you can see, you can check, but actually for whatever state you are measuring from these two states, their probabilities will be identical. So that means in the lab, whatever kind of measurement you are doing, the outcome is going to be the same. So for intents and purposes, it's the same state. There's no way of differentiating them in the world. And this difference here in the minus sign in front we call a global phase, and we usually just ignore them because it doesn't really matter. But for plus and minus, right? Or between the state plus and minus, their difference is also only a difference of 1 negative sign. So for plus it's 0 plus 1 square root of 2. For minus it's 0 minus 1 over square root of 2. So it's a difference of 1 negative sign only also. But for this case, the plus and minus states correspond to different, like in an actual experiment, you don't give the same probability for all measurements. For example, if you try to measure plus from plus, you'll get 1. Like every time if I give you a plus state and you try to measure a plus state from that state, it will definitely give you the plus states. Meanwhile, because the inner product of plus and minus is 0, the probability of measuring plus from a minus is 0. So they give different probabilities. So the probabilities are different, so they are not. So there's a way to distinguish them in the lab. So they are not the same state. And in this case, the difference of a minus sign, we call the relative phase, and that one you cannot ignore it. Second thing, when I've heard that in quantum mechanics, there's a wave function collapse. Measurement changes the state. So if I, so it's confusing, but you ignore this slide. You have deleted it. Basically, right, you can ignore the slides. It's too mathematical. You should change it. If I give you a generic state psi, then you do a measurement. You want to ask whether it's in 0 or it's in 1. And then after the measurement, you find out that it's in the state 1. No matter what the original state is, the next time you measure it, if you try to measure 1, you'll definitely get 1. And if you try to measure 0, you will definitely, well, you won't be able to measure 0 from 1 because they are orthogonal. So the point is, after the measurement, if the outcome is 1, the state actually changes to 1. Even though in the original one, it might be a superposition of 0 and 1. But once you have measured it in the 0, 1, and then you get an outcome 1, the state will change to 1. So this doesn't happen in classical mechanics. If you measure the length of this table to be 1 meter, it won't magically change its length to 1 meter if previously it was not 1 meter. But in quantum mechanics, measurement changes the state, and it's something that is inherent to the theory. It's not because of our limitation of our equipments, but it's a feature of the theory. And finally, in this example I gave earlier, the example was you either measure it in 0 or 1. So when we measure a thing, we always measure it in a basis, in some basis. In this case, it's a 0, 1 basis. And this basis must always be orthonormal. You consider if hypothetically I can measure in 0 or plus. So 0 and plus are not orthogonal because the inner product of 0 and plus is 1 over square root of 2. So it's not 0. So, but they form a basis because remember the linear algebra, they span the whole space. If you take the broad, now consider that I have a state 0 and I want to measure in this non-orthonormal basis. The probability of measuring 0 from 0 is 1. The probability of measuring 0 plus from 0 is 1/2. So you soon get into trouble because 1 plus 1/2 is 3/2, and 3/2 is larger than 1. And in probability, the sum of the probability of the outcomes must sum up to 1, not more, not less. It's like saying that a coin has a 70-70 probability of heads and tails. Doesn't make sense. So the reason why we measure in orthonormal basis is because the rules of probability. 5 minutes break. And we'll continue at 10:19.
All right, everyone, come. Yeah, break's over. Let's continue with the lecture. Yeah, so I'm Nigel, and I'll be helping Peter to finish up the slides for today. So okay, so technically it's still correct because you're going to take a break from the math. Let's slow down, smell the rollers a bit, digest what you have learned so far conceptually, All right. So okay, so in this section we'll pose the question to you guys. What's so special about this, right? What's so special about quantum measurements and this kind of random probability events, right? Don't we have like, yeah. So for example, if we take this state, you measure in the computational basis 0s and 1s, right? Yeah, so as Peter has already mentioned, there's a 50-50 chance you measure either 0 or 1 if you start off with this plus state over here, right? Yeah, so then so what's so special about this? Because don't we have random probability events in real life, right? So for a coin, for example, you consider a coin toss, right? It's a coin toss is similar to a quantum measurement, right? Aren't there like two different values, heads or tails? And when we do a coin toss, we think like, what's the probability of a coin toss? It's also like 50% heads, 50% tails, right? Right? If you want to, and also if you want to become you think more complex, right? You can think about meteorological events, weather events, right? It's also a very classical event. On the weather forecast, the news anchor will tell you like maybe there's a X% chance that there will be rain tomorrow. It's also a random event, right? But then I'd like to pose a question to you. Is a coin toss really random? Right? Is there any way that we can predict the outcome of a coin toss? Like, what if you had superpowers? What if you had the supercomputer? Right? What if you could what if you could do this? So I'd like to show a clip from the classic anime. It's No Game No Life. I hope you can see the subtitles. Yeah. Yeah. So if you couldn't see the clip, right? It's basically this very OP character that can somehow calculate all the dynamics and all the kinematics of a coin as it's falling down. Then with all the calculations, with a supercomputer, actually you can predict how a coin will land 100% of the time. So yeah, so I ask you the question again: is a coin toss really random, or are we just ignorant? Right? If we knew everything about the world, then we could predict these events with 100% certainty. And herein lies the special thing about quantum mechanics, in that I like to propose that you cannot do this with quantum mechanics. Even if you have infinite power and infinite computational power, there is no way you can predict whether a plus state will give you a 0 or 1. It is truly a 50-50 chance. Alright, so we move on to this. I'd like to drill in this point further with this Schrödinger cat experiment. Has anyone heard this experiment in like popular media, like in the movies, in like anime, stuff like that? Anyone? Yeah. I'm pretty sure, yeah. Pretty sure. Okay, so I'm pretty sure they have said it before, but for those who are not too sure what a Schrödinger experiment is basically we have let's say we build this isolated box and put in a cat, right? And we also put in a vial of poison that has a 50-50 chance of being broken, releasing the poison and killing the cat, which is actually quite morbid and cruel, but yeah, that's how the cookie crumbles. Yeah. So then I like to pose the question: what's the solution to this experiment? Right? Before you open the box, is the cat dead or alive? Or, as how the popular media like to portray it, is the cat both alive and dead at the same time? Right? Is this solution correct? Right? Well, yes, but actually no, right? Because for this kind of like thought experiment, there's actually no concrete answer in the eyes of quantum mechanics so far. Right? Because this experiment is not meant to be like realistic or accurate or whatever. When Schrödinger actually proposed this thought experiment and asked his fellow scientists on what they think, he actually wanted to show how absurd this kind of quantum measurement rules are, right? Can you actually imagine a cat, such a big object, being both alive and dead at the same time? Wouldn't the cat know it's alive or dead, right? So if you actually think, right, and pose this question to yourself, right? Can you actually do this in real? Can you do this experiment in real life? Right. Well, the answer is actually with our limited technologies. Actually, no, we cannot do this experiment in real life. And in an actual experiment, if we do it, the cat is already dead or alive. It's already set for us in our modern technologies. Yeah, this is because similar to the coin toss thing that I explained earlier, there's actually if you had the technology, you could actually come up with some way to measure some clues and to tell you like the outcome of the experiment. Like maybe in this box, if the cat is alive, it's walking around right in the box, then maybe it will send like some minuscule vibrations through the box, and if your instrument is strong enough, sensitive enough, it can pick up this kind of vibrations, and you can actually tell, hey, the cat is alive, or there's no vibration, the cat is dead and it's not moving, something like that, right? Yeah, okay. Okay, yeah. So the question was, if you could find a clue about the cat's situation, then that's also counted as a measurement. Yeah. Yeah. So I mean, okay. I mean, we don't want to go too metaphysical about this, but then what counts as a measurement, right? Let's say we don't open the box. We don't try to find any clues about it, right? Is the world not truly measuring the outcome of the cat? Isn't the cat a sentient being? Isn't it measuring itself? Okay, yeah. So we don't want to get into that kind of territory. It's beyond the scope of this lecture. Yeah, I just wanted to tell you, ask you to think about these kind of things, and also don't trust popular media too much. Okay, now we have digested information, so we can go back to the math, right? Now we're moving on to something called operators. Right. So I'd like to tell you that operators are also matrices, but in the context of quantum mechanics, they actually help us to manipulate or change states, right? So let's say our operator is this big A over here, is also a matrix. Let's say we multiply it into this cat vector psi over here, right? So the definition of operator is that you will satisfy this equation. It may or may not change the state. It may give you a phi, but it will also give you a scalar multiple in front of it, right? So that's the definition of operator, right? And similar to the state vectors, operators can be represented by matrices, right? Yeah, for us, we use 2 dimensions, so it's just a 2 by 2. Right. Then as you might have tried your hand at yesterday during the tutorial, you can also diagonalize these operators. So you can split them up. You can split them up into the different basis states, each with its own A, the eigenvalue, and these are eigenvectors, right? And then you can just put it as a sum of all of them, and you can reconstruct your A. Yeah. Okay. So in this lecture, we will give you 2 types of operators. The first type is a unitary operator, very important. So these unitary operators, right, they have the definition in that they preserve the inner product between states, right? So as you have heard from Peter just now, these inner products, they can give you a clue on like probability measurements. Like if you measure one state, what's the probability that you measure as the other state, right? So it's just a definition thing, but if you follow this equation over here, right? This inner product over here doesn't change after you apply U, right? So that's the definition. Yes. So this gives us a very nice equation over here. U dagger, which is just to remind you, dagger is transpose conjugate, and U if you multiply them together, it gives you this I, which is the identity matrix. So the identity matrix is literally just 1001, right? What it does is that it does nothing. Okay, if you multiply I to the state, right, it will give you back the same state because it's literally a multiplication of 1. It's no change. Right? So I like to show you a very interesting interesting fact about unitary operators is that in general unitary operations are reversible. So what do I mean by this is that if you apply a unitary U to a state, there is some way to bring it back to where you started. Right. So okay, let's look at this. Let's look at this equation I showed just now. So you have U dagger U equals to I, right? But what you can do is you can bring this U over to the other side of the equation. You get U dagger equals to U inverse. So just to remind you, an inverse matrix is basically how you reverse the operation. You can bring it back to where you started. Right. And wait, there's more. So if U equals to U dagger, if you compare the two matrices and they're the same, then by this definition, right, U inverse equals to U itself. So the reverse operation equals to its own operation. So in that case, we can undo any operation by applying the exact same operation twice, right? Okay, so we'll go. Okay, don't worry, we'll go through an example later. All right, first, I just like to show you some examples of unitary operators. So we have these 3 sets of matrices over here. You might see them in your tutorial yesterday. These are actually called the Pauli matrices. Right, they're just 3 sets of matrices. They are arranged by the spatial dimensions X, Y, and Z. And also one such example is called an Hadamard matrix. We use H to represent this matrix here. Okay, so let's go through the example that I promised. So let's say we have a random, let's say we have this random arbitrary state. We have an AB state, right? And we apply X to it. X is the power matrix I showed just now. Right, so what happens to it? All right, you go through the matrix multiplication math, take this, multiply this, and at the end you get BA. So what does the X gate? What does the X operation do? Yeah, it just flips the two probability amplitudes. Right? Cool enough? All right. So, and just now I also showed that unitary operators are reversible, right? So let's go through this example. So let's check what is X dagger, right? What's the conjugate transpose of X? If you look at this matrix over here, the answer is there for you. I explored it for you. It's actually the same because this matrix is completely real and symmetric about the transpose. So X dagger equals to X, right? And I said before, if you apply the X gate again to this BA, we take this state and apply X again, we get AB. So we have come back to our original state. Wow, so cool, right? Yeah, okay, so in general, yeah, unitary operators in quantum mechanics, we use it because we want to model like a physical phenomena, right? So some examples are, so the identity matrix is also a unitary operator and actually is for you to do absolutely nothing. So that's the most simple example. You also can use unitary operators to model time evolution. So let's say we just have a state and we leave it in like the lab for like maybe a second or so. You might see that these states actually evolve in time and change. So you can actually model it using unitary operator here also. Gonna be even more complex. You can also just have a spin system, as Peter has shown before, and you can actually rotate the direction of the spin. Yeah, so that's also a unitary operator. Okay. However, there's the next, there are other operators which are not unitary. What do you think is it? Any guesses? Okay, give you the answer. Yeah, it's called measurements. Woo. Yeah. Yes. So we segue into our second type of operator, which is the Hermitian operator. Right. So this is the definition over here. The conjugate transpose, the dagger, equals itself, similar to what you see just now. And also you similar to unitary operators, you can also diagonalize and split them up into these eigenvalues and eigenvectors, right? Okay. However, now this is the difference in that Hermitian operators, we usually use it in the lab to measure something, to measure observables. So so if you look at this equation over here, these A vectors, they are the eigenvectors, yeah, but they actually also represent the basis of measurement. And the A in front here, the eigenvalue, is associated with the measurement value, the result, right? So for example, we can measure energy. The most common example is energy. So the A is our energy, and the A dagger is the state that has that energy. Yeah, okay, we'll go through example later, don't worry. Yeah, this example. Yeah, okay, so let's take an example of a Hermitian operator. You can pick this thing called a spin Z operator. Right, so remember what Peter said before? Like electrons, they have their own spin, and the direction actually matters. The direction of the spin actually matters. And we can measure this using this SZ over here. So it's just 1, 0, 0, -1, h bars over 2, right? Okay. So then we can diagonalize it into these two terms over here. And what do they mean? Right? Wait, arrow. Okay. In this form, right? So we have a plus Z and a minus Z. So this just represents the two different directions of spin that we are interested in. So this plus Z, let's treat it as this thing, as this kind of spin. So what this arrow means is that, all right, remember your right hand rule, guys? Right hand rule. So you put your thumb in the direction of the arrow, right? And in your mind, you can just imagine that it's so-called rotating in the direction your fingers are curling, right? It's not super accurate, but you can just imagine it like that for now. Yeah, and this minus Z is the opposite direction. Simple enough, right? And then we have this h bar over 2 and this minus h bar over 2. So this spin has an energy of plus h bar over 2, and this spin has an energy of minus h bar over 2. They are associated and tagged to each other. So this is the energy observable. Yes.
Could you explain how this relates to eigenvalues and eigenvectors?
Okay, yeah, sure. So as I explained before, we have diagonalized this to these two terms, and yeah, so this matrix has two eigenvalues and two eigenvectors, right? So we can split into two terms, and these are actually the eigenvalues that you can extract from this matrix over here, right? The eigenvalues of this matrix will be plus h bar over 2 and minus h bar over 2. And then you can, if you remember your tutorial yesterday, you can find the eigenvectors that satisfy this equation. And you get two eigenvectors, which is what we have labeled as plus Z and minus Z, right? And yeah, and then you can use this to connect it to this picture over here to have a physical meaning of like what are, so a physical meaning of eigenvectors and eigenvalues, right? Just a recap just now, eigenvalues are the measurement outcomes, the eigenvalues are the states that have that outcome. Is that clear? Okay. All right. So how do we calculate this kind of measurement outcomes? If we calculate something called an expectation value. So expectation value is calculated using this. Simple enough. You just have the state that you want, and then you sandwich it. You sandwich it with the Hermitian operator in this case. So let's go through an example, right? Yeah, example. Alright. So we go back to the spin Z state, right? So now let's calculate a expectation value, right? So remember we have the two states sandwiching the SZ. So let's sandwich the SZ with plus Z and plus Z onto the two sides, right? So to translate this calculation to English, right? We're actually measuring what is the expected energy of this spin up state, which is the plus Z. And if you go through the calculation, you get h bar plus h bar over 2, which is what we expect, right? Because this is the associated eigenvalue. If you do the calculation again with minus Z, you get minus h bar over 2. Also expected, right?
In this case, does the plus Z and the minus Z correspond to the 0 and then?
The 0. Okay. So remember what? Okay, so just to recap what Peter said, these alphabets and numbers and symbols in the vectors over here, they are just notations, right? Yeah. So in this case, if you want to, you can also treat this plus Z as 0 and minus Z as 1. Yes. Very convenient. Okay, so now let's kick this up a notch, right? So how about we measure it using a different state? What we use a plus X, right? Okay, so we define this. So similar to these over here. Let's define this plus X as a plus Z plus minus Z. So it's a superposition state between the two Z states, right? So in your mind, you can imagine your ball or your electron spinning sideways now, right? Instead of up and down. Somewhere, yeah. So what do you expect? What would be the expected energy out of this? Any guesses? Remember for the plus Z, we have a h bar over 2 and minus h bar over 2. 0. Okay, very good. So let's go through the calculation. So we follow the same steps. We sandwich that state between the two plus x's. But because this plus x is a sum of these two, we can also split up the calculation into two parts. Plus h bar, plus z and minus z. And you just take these results over here from the top. You get plus h bar over 2 minus h bar over 2, you get 0, right? So physically, does this make sense? Right? Okay. So if you translate it to English a bit more, to physical meaning. So basically, you're measuring this state, right? What's the chances that you measure it as a spin up? 50, okay, 50% chance you measure this state as a spin up and spin down because we measure it in the up and down basis, correct? Which is what we have gone through before. So 50% chance you get h bar over 2. 50% chance you get minus h bar over 2. So if you average everything out, you get 0. Ta-da!
How do you know it's 50% based on that? Is it because 1 is like the negative?
Okay. If you want to think of it as a physical picture, this direction, this vector, this sideways vector, is exactly halfway between up and down, right? If you take an up state and then you rotate it downwards, right? The midpoint is half, right? So that's the physical picture, but of course you shouldn't trust your imagination too much. You actually should, if you want to, you can also mathematically prove this by taking your matrices and then doing the Bond's rule again, right? Same thing. Let me write it a bit higher. Should have asked first. Right, so bonds rule again, right? You want to prove that you get 50-50, right? So what you do is you have your inner product state, right? Of plus z and plus x. Then you put a square modulus bonds rule, correct? Then you can expand it. So you know your x state can be split up into two z states, right? So you split this calculation up. You have a plus z, and then a plus z minus z. Right? Right? Yeah. Okay. Yeah. Right? Then what is this? What is this plus z plus z? There's one. What is this plus z? Inner product minus z. Remember they are complete opposite directions. Yeah, 0. Right? And at the end, you get upper. Yeah, that's the yeah. Yep.
So likewise, you can prove for plus z minus x to get the other half.
Sorry. What?
Like you could change the plus x to minus x to prove the other half, is it?
Yeah, you can do that. I leave that as exercise to you. Yeah, it's actually very similar. I don't have to go through it again. Yeah, so actually we have reached the end of the lecture. So let's go through a bit of a summary again. As you have learned already, qubit can be described by this sum of two states. A and B can be your any probabilities you want, as long as at the end you end up with modulus square 1. Yeah. Then given random any state you want, and you can the probability of measuring this other state is just given by this bonds rule over here. Yes. And yeah, operators. You have two operators, unitary operators. You just need to know that mathematically this is the most important definition for unitary operators. U dagger U equal to nothing, right? And then formation operators, they measure something. You measure something in the lab. U dagger equals to H. And to calculate the measurement results over many different experiments, and use this equation over here. Yeah, I think we're done. Yeah. Yep, we're done.